Hello everyone. Today inshallah we will continue the antiderivative topic that we already initiated in the previous session. Today I will talk about integration by parts and we will continue for the integration by substitution. I think this was the last thing that we spoke in the previous session. And also I will continue to the definite integration, the Dropbox theories, and we will go from there. So please focus and try to solve as much problems as you can, because as I told you previously, it's a skill. It needs a continuous training, as we spoke earlier. I think, inshallah, by the end of this lecture, we will be able to go through rational antiderivatives, and we will go for the beginning of the definite integration, inshallah. So I would still have the message that I usually repeat before we start every lecture. All of our course notes references, you will find them on Moodle, and also the recorded lecture, you will find them on YouTube. Once more, to the 1,000 times, please go to Moodle. You will have a lot of information over there, new topics to be read, and also you will have supporting videos about each topic that we are talking about. I will start with the idea of the antiderivatives and the idea of integration by parts that we already initiated in the previous session. But before we go through this, I want you to remember the main formulas that we are using in integration, which actually not much. They are a few rules that I want you to keep in mind in all times. Of course, the first of them is the integration of f dash of x times f of x to the power of n with respect to x. The answer is going to be really, very simple. Once this condition is already there, then the result will be f of x to the power of n plus 1 divided by n plus 1 plus the constant of integration. That's golden rule for us. Also, the second rule, which is really, very important, this is applied, or this rule we can apply for every value of n except at n minus 1. If I have f dash of x by f of x with respect to x, then the integration will be ln f of x plus a constant, as you can see, and also it's really a very direct relationship. And we also took in the previous session the integration of an exponential function e to the power of f of x times f dash x with respect to the x. So the integration will be e to the power of f of x plus a constant. Number 4, if I want to integrate f dash of x times a to the power of a f of x with respect to the x, also the integration is very, very simple. It's going to be a to the power of f of x divided by ln a plus a constant. We really solved plenty of problems on all of these rules in the previous 2 sessions. It's very, very important to go through this and once more to keep them in your mind. Also, we took the rule of integration by parts. If you remember, if I want to, I usually give it this way, if I want to integrate 2 functions multiplied in each other, okay, I usually choose one of them to be integrated, the other one to be differentiated. So simply, if these functions are already under derivative sign, then I will have u of x, which is the integrated part, time v dash of x minus integration u of x times v double dash of x with respect to the x, and we had the application on either exponential function or trigonometric functions. In this slide, you will have the opportunity to review, okay, and to understand more about how the main law of integration by parts came from. And we will have also a couple of problems in which we can apply integration by parts. As I told you, integration by parts is dedicated for the process of multiplication of functions. So mainly, if you remember, the rule of the differentiation in case of two functions multiplied in each other. So if I have two functions multiplied in each other and I want to integrate, all I have to do is to find, if we want to differentiate, I will differentiate the first function times the second plus vice versa. That's actually what's happening. We have differentiated the first function, which is u dash of x times v of x plus u of x will be the same, then differentiating v of x, which is v dash of x. From this flow, if we want to reverse the process in integration or antiderivative, then integrating the derivative will eliminate the derivative. So I will have u of x times v of x, integrating the function with dash with respect to the x, so they are similar. This will lead to the integration of this part. So once more, in order not to lose the attention, if I am integrating the left-hand side, it means I'm integrating the right-hand side, and of course it can be, as you can see, distributed on the two parts. In order to get to the final form, I will move this part to the other side. Of course, integration of a differentiated function will leave you with u of x times v of x this term. And I will move this function or this part of my two right parts to the other side, which is going to come up to u of x dot v dash of x dx. And it's all equal to this integration. This is the integration by parts rule, and as you can see, I will choose this function to be integrated while I'm keeping this one to be differentiated. So integrating the first function, the second, minus integration, the function which is integrated is the other function will be differentiated. That's the main rule of integration by parts. As I told you, it's really very simple rule. We can apply it, as we saw in the previous session, on three main cases. Case number one, if you have a polynomial times exponential of trigonometric function. Case number two, if you have a function that you cannot integrate. If you have the third case, if you have two continuous functions in differentiation and integration, the general case is like multiplying exponential function in trigonometric function. Okay. Before we go further, I want to show you this problem, which I want to integrate, to find the integration of x times e to the power of 2x times dx. Just to try solving using integration by parts. In order to integrate this function, all I have to do is to choose one of these two parts, the first part and second part, to be integrated, and the other part will be differentiated. So all I'm going to do is to choose e to the power of 2x to be integrated, because this is case number one regarding the cases of partial integration by parts. So I will start this part by integrating and leaving the polynomial to be differentiated. Let's do it together. Integrating e to the power of 2 over x. Of course, integrating e to the power of 2x, I will need to multiply by 2 and divide by 2 in order to get the form of integration of an exponential function, which will leave me with e to the power of 2x divided by 2. That's the part that will be integrated. Times the second part, which is simply x. Then minus integration. The function that I need to integrate, it's already done, so it will go down, which is e to the power of 2x with respect to x and that's the half outside. Then the other function, which is x, I will differentiate. So differentiating x, it will be just only 1. Now I will finalize my answer. So it's gonna come up to x dot e to the power of 2x over 2 minus a half. Then I will have to integrate once more e to the power of 2x, which is simply gonna be e to the power of 2x divided on 2 once more plus a constant of integration. Then the final step is to have x dot e to the power of 2x over 2 minus e to the power of 2x divided by 4 plus a constant of integration, as you can see, which is really a very important application on the integration by parts. There are tons and tons of problems, plenty of problems that's actually dedicated for the integration by parts, and the ideas is massive. Even the substitution method, sometimes when we make our substitution, it will get back to be an integration by parts problem. This is why it's really very important just to watch it and to go through it. I would like to show you some of these problems. As I told you, the major issue is to decide which method of integration that you are going to use. So usually the main obstacle or the main problem in integration by parts, it's not, not in integration in general, not just knowing which method, but choosing the right method to be applied in this case or in the problem cases. So if I look to the first problem, which is the integration, okay? I'm talking about problem number A. I'm talking about this problem, in which I want to integrate x times the root of x plus 1. Of course, before going through this problem, I would like to draw your attention to a problem on this form. I want to integrate x times square root, almost the same problem. All I have to do is just to add x squared dx. If you look to this problem and to that problem, you will discover that the only difference is the power. This is power 2, but this is power. In order to integrate this problem, of course, this is much easier, okay, in integration, because simply all I have to do is to put it on this form. It is the integration of x times x squared plus 1 to the power of half with respect to dx. On this particular form, if you remark that the derivative of what's inside the bracket is 2x, which is a condition for this process to be integrated. So I need to find 2x in front of this huge bracket. So at the time being, it seems to me that already I have partially the differentiation of the function inside the bracket. So all I have to do is to multiply by 2 and divide on 2. So the integration will be a half integration of a 2x for x squared plus 1 to the power of half with respect to the x. The condition is satisfied, so directly I will apply the rule, which states that x squared plus 1, I will add 1 on the power, which is going to be 3 over 2, divide on the new power, which is 3 over 2, and of course all of this is multiplied by 1 over 2 plus the constant of integration, just simplifying, knowing that denominator of a denominator is a nominator. So simply I will be x squared plus 1 to the power of 3 over 2 divided by 3 plus a constant of integration, as you can see. This is really major. Remark how the ideas are integrating together, or the ideas integrated together in order to lead you to the right action for solving the problem. If I look on the other hand, to this problem, it's completely different setting. Because as you can see, x plus 1, the derivative is equal to 1. And then instead of 1, I have x. So in this case, I will have to think of another method of integration. So instead of integrating in this manner, I have this function which states that I is going to equal to the integration of x times the root of x plus 1 with respect to dx. Okay, so at this time I will try integration by parts. So I will consider the second part, which is a root of x plus 1, to be on this form, which is going to be much easier on me on integration x plus 1 to the power of 5. Then I will choose which one of these two functions will be integrated and which one is going to be differentiated. So I will choose this part to be integrated and that part to be differentiated. So once more, I is going to equal to, I will integrate this part, which is going to come up to x plus 1 to the power of 3 over 2 divided by 3 over 2 times the first part, which is x, minus integration. Okay, rearrange your thoughts and what you did before you continue. So the first part is going to be 2 over 3, which is a constant. X plus 1 to the power of 3 over 2 will go down. Okay, I'm going to changing them. But this is the part that will be differentiated. So differentiating x is going to be positive 1. So once more, I is going to be 2 over x. X plus 1 to the power of 3 over 2. All of them divided by 3. Then minus. Once to integrate this function, I will add 1 on the power and then divide on the new power. So it's going to be 2 over 3. And once more, I will have x plus 1 to the power of 5 over 2 times 2 over 5 plus the constant of integration. So I will be 2x times x plus 1 to the power of 3 over 2 divided by 3. Then it's going to be negative 4 over 15 times x plus 1 to the power of 5 over 2 plus a constant, as you can see. This is exactly what I'm telling you. This is how it should be done. And this is really very important. You will have to resolve it, to capture the idea. What's the difference between a problem and the other? I hope this is clear for you. In a similar manner, I would like to solve the second problem. So we will go through it together, inshallah, with the same sequence. So if I'm trying to deal with the second problem, so simply, as I told you, I wanna integrate x squared times e of x dx is exactly like the previous, okay, details or the previous debate. This problem is easier or that one is easier. The integration of x squared times e to the power of x to the power of 3. Which one of them is easier to deal with? If you take just a moment and look at these two functions, I'm dealing with an exponential function times a polynomial function. So I'm actually searching about the form of the law. The form of the law of integration states that if you have e to the power of f of x and it's times f dash x phi dx, then the integration will be e to the power of f of x plus a constant. So I need to check. So if you look to this problem, probably the derivative of the power is really very simple, which is 3x squared. The only issue to check if this value of this exponent already exists or not. As you can see, I have x squared, but I'm missing positive 3. So all I have to do now is to multiply n3 and divide on 3 the polynomial part and consider my function. It's going to be exactly on the rule. So I is going to be e to the power of x cubed over 3 plus the constant of integration, and we are done. But unfortunately for this problem, this is not going to happen because you have x to the power of 2 times e to the power of x. And the derivative of the power in this case is just only 1, not x squared. So in this case, I will have to integrate, but using the integration by parts rules. So I will choose one of these two functions to be integrated and the other function to be differentiated. So once more, I will integrate e to the power of x and then differentiate x squared. I will go with this rule, integrating one of them and differentiating the other one. Fortunately, e to the power of x, the integration will be e to the power of x. So integrating e to the power of x, it will remain e to the power of x. Times the second function will remain the same. X squared, it is x squared. Minus integration. The function that I needed to be integrated, it's going to be e to the power of x dx. The other function will be differentiated. It's going to be 2 times x, as you can see. I will repeat the integration, so I will be x squared times e to the power of x minus 2, and once more I will integrate. Integrating e to the power of x, which is going to be e to the power of x, times the second function, which is x, then minus integration. Okay, the function that I already integrated, which is the exponential part, then the other function, which is x, I will differentiate, which is equal to 1. And then I will finalize all of this. So I will be x squared times e to the power of x minus 2 over x e to the power of x plus 2 e to the power of x plus a constant of integration, as you can see. So in this case, I've applied the integration by parts. How many times? I've applied it 2 times. Remember, in applying the integration by parts more than once in one problem, the part of the functions that you are integrating, keep integrating, while the other part of your functions that you decided to be differentiated, keep it differentiated till you finish your integration sign, or to get rid of all the integration signs, as you can see. The third case here, it is the integration of len of x. And the integration of len of x, you are not going to be able also to integrate this function unless you have the derivative of the bar of this function already with you. If you don't have it, you are not going to be able to integrate. So, for example, once more I need to integrate, and this is one of the problems that we already solved in the last session. If I want to integrate len of x, and if I want to integrate, for example, len x on x dx, which case of them is more simpler than the other? Yes, you are right. It is the one on the right, it's much simpler because it is simply will equal to, it is the integration of len of x times 1 over x with respect to the x. So this function derivative already exists. So all I have to do is to state that I equal to len of x increase on the power and divide on the new power plus the constant of integration. So all I have to do is to just consider len of x increasing on the power by 1 and then dividing on the new power, as you can see. So it's a len x to the power of 2 divided by 2 plus the constant of integration. While in this problem, I can't do that because the derivative of len of x does not exist. So simply, I will make this trick. I will consider len x to be multiplied by 1. So all I have to do at the time being is to differentiate ln x, which I can, and integrate the other part, which is 1. Let's try to do it. So I is gonna be simply integrating 1, which is gonna be x times ln of x minus integration. The part that's integrated, which is simply x. The other part, which is ln x, let's differentiate, which is 1 over x with respect to the x. So I simply will be x ln x minus, this is just an integration with respect to the x, so it's going to be x plus a constant of integration, and that's the integral of the ln of x, as you can see. Those problems, and as I told you, there is infinite number of problems. I'm not just exaggerating, just changing anything, and you will have your functions. It needs skill of just memorizing the relation between functions, and as you can see, the experience in solving the problems. The second part that I would like to talk to you, it's considered a new part, it is the substitution method. The rules that we are using at the beginning that I gave you by the beginning of this part makes you or enable you to avoid as much as possible the substitution. The substitution strategy is to choose in your problem the part that has maximum issues or a problem in it, and try to give it an assumption. Okay, but there is a price that will be paid in this case, which is simply you will have to find the relation replacing the integration with respect to x in order to satisfy your equation. So in order to do substitutions, I will need to change something or all the variables in f of x, and I will pay the price that I will also replace dx by a certain relation with respect to t. So this is why it is really very important to keep in mind these problems. So I want you to see those problems and how we try to speculate them. I have 4 problems. They are really very good to transfer the idea of how to integrate. So if I look to the first of them, which is I want to integrate e to the power of root of x with respect to dx. If I want to make substitution, I will start to think about the part that bother me. And then I will try to make a substitution to get it go away. But at this time, I will have to keep in mind that I will change dx also. So in my case, I think it's a very good idea, since we have square root, to put x is equal to 2 squared. So this came into my mind because I want to break the square root. So if I put x, let x is equal to t to the power of 2, this means that dx will equal to, find the differential for the equation, it's going to be 2t times dt. So now I'm substituting each x by t squared, and there is a price to be paid, which is replacing the dx by 2t times dt. So if we did this transfer or substitution, my new problem will be, it is the integration of e to the power of t squared, and in this case I will replace dx by 2t times dt, as you can see. So once you put t squared instead of x, it's under the square root, and I've replaced dx by 2t dt, then I will have the integration of 2t times e to the power of t with respect to 2t. And in this case, I will need once more the integration by parts in order to solve my problem. So simply, all I have to do is to choose e to the power of 2 to e to the power of t to be integrated, and the other part, which is 2t, to be differentiated. So let's do it this way. So I is going to be integration e to the power of t is going to be the same times the first part, which is 2t, minus the integration. The integrated part, which is e to the power of t, it will remain untouched, where 2t, once you differentiate it, it's going to be simply 2, and then stuck with this integration also, which is direct. The integration of e to the power of t is e to the power of t, so I will have 2t times e to the power of t minus 2e to the power of t plus the constant of integration, as you can see. It's very simple and smooth. And then I will need to reverse my substitution. So from this part, the x is equal to t squared. It also means that t is equal to the absolute, that t is equal to positive or negative the root of x, or it is the root of x, as you can see. If you take square root for both of them, then I will make the substitution once more. So I, it's gonna be 2 root x, sorry, I will replace every t by root of x, 2 root x times e to the power of root of x minus 2e to the root of x plus the constant of integration. As you can see, the substitution give me a scale, or prepare the scale from me, an action, in order to integrate this function. Without this substitution, this problem, it's going to be very, very difficult, or even it's not integrable, since we don't have the derivative of the power already exists beside e to the power of root x, or we didn't use integration by parts by the beginning of this problem. So once more, as you can see, it's really very simple. All I have to do is to choose the right substitution. So this is for problem number A. If I want to repeat it, and that's the new part, which is the change of variable due to my substitution. Let's try the second problem. Let's see the second problem. Okay. So, the second problem is I equal to the integration of ln x to the power of 2 with respect to x, as you can see. If I want to integrate this problem, okay, I have a problem, which is I don't have the derivative of ln of x. So once more, I will put ln x is equal to t. This is the idea. I'm searching for the part of my problem that causing me all the problems, or it is the not very nice part. So I will try to let ln of x equal to t. Once you did this, I will need to have x in one side. So simply, I will change the logarithmic form to be on the exponential form, which means x is equal to e to the power of t. And then, once more, I will differentiate both sides, which will leave me with d of x is equal to e to the power of t times dt. Then, I will choose this rule in integration, or I will start substituting in this manner. So, if I try to do this, then I will have I is going to equal to, I will replace every ln x by t, so I will have t to the power of 2. Then I will replace dx by the other part, which is simply, it's going to be e to the power of t times dt, as you can see. And once more, we head back to integration by parts. So just applying the rules of integration by parts once more. So starting from here, I will use integration by parts, as you can see. So I will choose once more e to the power of t to be integrated and t squared to be differentiated. So once more I will repeat this. So I is gonna equal to integrate e to the power of t, it's an e to the power of t, times the second function will remain the same, which is t squared minus integration. The integrated part will go down, e to the power of t, so with respect to t. The second part, which is t squared, I will differentiate, so it's a 2 times t. Once more, I will finish this integration. So I is gonna equal to 2t squared e to the power of t. Then I will have negative 2, open your bracket, and start integrating. Once more, e to the power of t will be integrated, while t will be differentiated. So integrating e to the power of t is going to be to the power of t times t minus the integration t derivative is equal to 1, and then I will have e to the power of t with respect to t, and finalizing everything by the rule, which is t squared times e to the power of t minus 2t e to the power of t plus 2. Then negative, of course, times negative is positive, which is really very important to take care about the sign conversion and what's happening in your problem. Then this is going to be to integrating e to the power of t, it's an e power of t plus a constant of integration. And once more, I can reverse this process. How to reverse this process? Every t can be changed to the x, and every e power t can be once more changed to bx. So if I want to make a change of variable to get back to the original variables, I will change t with ln of x. So it's going to come up to ln of x to the power of 2. Then I will have e to the power of t, which is simply x. Then minus 2, this is minus 2. I will replace t by ln of x, as you can see.